तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
In the last lecture, we were considering the solution of the homogeneous matrix equation of the form x dot equals Ax, where x and x dot are n vectors, column of n entries, A is a square matrix of order n by n. We said the solution for this can be put in the form x of t equals e raised to the power of at times x0. This is x of t, and we said that e to the power of at is itself a matrix of order, square matrix of order n, and e to the power of at can be put in a more compact form as phi t x0. x0 is the initial state, xt is the state at any point of time t, and phi t or e to the power of at, they are called the state transition matrices. This is another way of indicating e to the power of at. The state transition matrix or simply the transition matrix. And the first thing we have to do today, this lecture, is to find out how to evaluate phi of t for a given A. We also said that if the conditions of the state is not given at t equals 0, but at a point say t equals t naught, then we can also write this as phi of t minus t naught times x at a point t naught. This is also another way xt can be derived from this initial state at t naught instead of at t equals 0. Now the way to calculate e to the power of at, there are several ways of doing this. So we will start some methods of evaluation of e to the power of at. You may recall that in the Laplace transform domain of an equation like this, we said in the Laplace transform solution of the state equations, the Laplace transform of the state xs, you recall, has been given as si minus a inverse x0. This is the zero input solution. The zero input solution of the state in Laplace transform domain x of s will be x of s si minus a inverse x0. This is a constant vector. Therefore, whatever we are having here must be the Laplace transform of this, because we have taken the homogeneous equation, we said u equals 0, therefore this is whatever solution you get for the state is a zero input solution. So this is the equation transform domain. In time domain the equation is x of t is e to the power of at x0. So this should correspond, these two must correspond to each other, which clearly, therefore if you take the Laplace transform of this x of s times the Laplace transform of this times x of 0 being a constant. Therefore from these two equations we therefore see that e to the power of at must have Laplace transform si minus a inverse. So e to the power of at, Laplace transform of e to the power of at is Si minus A inverse, or we can say Si minus A inverse that is what we have said. Therefore, to get e to the power of at is the inverse Laplace transform of Si minus A inverse. So, one way of finding out e to the power of at is to form the matrix Si minus A, take its inverse, you have a denominator which is the characteristic polynomial, and each term you take the inverse Laplace transform, taking the denominator also into account, and that will form the matrix in time domain which correspond to e to the power of at or phi t, which is the system transitional matrix. Therefore, the Laplace transform domain we see that phi of t and Si minus A inverse form a transform pair. This is one method of doing this. But however, we would like to work out the solution in time domain, and there is not much point in now shifting to transform domain and coming back to the time domain in the final solution. So, while this is an alternative way of doing this, this is not a time domain solution. So, we would just indicate this to show the relation between phi t and Si minus A inverse, but we will not pursue this at this point of time. The second method is to take the infinite series for e to the power of at. So, we say that e to the power of at is the infinite series. I is a unit matrix of dimension n, at plus a squared t squared by 2 factorial, a cubed t cubed by 3 factorial, and so on and so forth. This is the infinite series expansion for e to the power of at. Therefore, you form a squared, a cubed, and try to add up these terms because all of them are square matrices of order n. They are compatible for addition. Therefore, you can think of calculating e to the power of at by taking the infinite series for each one of these terms which are present in this matrix, which is present in this matrix. And for the useful systems where stability is ensured, this is a convergent series. Therefore, depending upon the accuracy which you need, you can go up to a certain number of terms and stop there. However, this approach will give you the solution perhaps in a very good way for numerical work, but it will not give you a closed form solution, and it does not provide you any particular insight into the behavior of e to the power of at, because you are getting just numbers. You can use it for calculation of numbers, but certainly you may not be able to put the final solution in a closed form expression as a function of time. So, this is one truncation of an infinite series at a particular point of time is one approach which is suitable for computer working, for numerical working, but certainly will not give a closed form solution. We leave it at that. Another approach is to diagonalize the A matrix. It can be shown that if you pre-multiply the A matrix and post-multiply it by appropriate matrices, T is a transformation matrix of order n. If you choose a suitable transformation matrix like this, whatever A matrix you get can be converted into a diagonal form. The diagonal form of the matrix will be, you have all the eigenvalues on the main diagonal and everywhere else the entries are 0. This will be the case when all the eigenvalues are distinct, no one is repeated. So, for distinct eigenvalues, and when such is the case, it happens that the transformation matrix will be a collection of rows, each row represents an eigenvector. So, we have n eigenvalues, you have n eigenvectors. And once you find this out, then you can write e to the power of at as t times again a diagonal matrix where the entries are e to the power of lambda 1t, lambda 2t, and so on, e to the power of lambda n t. This is again a diagonal matrix where the entries along the main diagonal are e raised to the power of lambda 1 lambda I t, where lambda is the eigenvalue, times t minus 1. So that will be the situation when all the eigenvalues are distinct, and in this case once you identify the T matrix here, you can calculate e to the power of a t by multiplying this diagonal matrix by t in one side and t minus 1 other side, and you get this. It gets slightly more complicated when some of the eigenvalues are repeated, but we will not pursue this particular approach. We will again just mention this as a possible alternative, and we will not pursue this anymore. The particular approach which we will consider is one which uses a theorem in linear algebra known as Cayley-Hamilton theorem. Now here we make use of this particular theorem which states every square matrix satisfies its characteristic equation. This is the statement of the theorem. What does it mean? Suppose you have a matrix A, a square matrix. Its characteristic equation is of this square matrix is determinant of lambda I minus a, that matrix equal to 0, which we said we can put it as f lambda equals 0. This is the characteristic equation. So the characteristic equation of this matrix A is f lambda equal to 0, where f lambda is obtained by making the determinant of lambda I minus k, where I is a unit matrix of order n. And if this matrix is order n, this polynomial f lambda is of degree m. So you have f lambda will be of the form lambda n plus say a n minus 1 lambda n minus 1 on up to a naught. That is what we are having. This is equal to 0. This is the characteristic equation. Now what this Cayley-Hamilton theorem states is, if instead of the characteristic equation as a function of lambda, if you set up the characteristic equation as a function of the matrix A, then also it is satisfied. That means this theorem states that f as a function of A, which means a raised to the power of n plus a n minus 1, a raised to the power of n minus 1, and so on and so forth, plus a naught I this time equals 0. So this is the scalar equation, this is the matrix equation. Here every term is a scalar, a particular number. Here every term is a matrix, a square matrix of order n, a to the power of n, a squared, a cubed, all these are matrices of order n. And the last term is also a matrix of order n, because we are putting a unit matrix. And the 0 on the other side is, this is also not a scalar, but is a matrix of zeros, a square matrix of zeros. So a solution of this characteristic equation is lambda, a scalar, but instead of lambda, a matrix, if you substitute a, that also satisfies the characteristic equation. That is the purport of this Cayley-Hamilton theorem. Now what is the consequence of this theorem? The consequence of the theorem is that if you looking at this particular polynomial equated to 0, matrix polynomial, a raised to the power of n can be expressed as a polynomial of degree n minus 1, because a power n equals minus of a n minus 1, a power n minus 1, and so on and so forth. So that means a power n can be expressed as a polynomial in A of degree n minus 1. So a power n can be expressed as a polynomial of degree n minus 1. That is not that's not all. Suppose I have a polynomial of higher order, then also it can be reduced to a polynomial of degree n minus 1. How it comes about we will see in a moment. Let us consider, for instance, a polynomial of very high degree, a grand polynomial, let us say of lambda, g lambda, polynomial of high degree, polynomial of large degree. Now this polynomial, suppose you divide this f lambda, the characteristic polynomial, into g lambda, we can write this as some quotient polynomial times f lambda plus a residual polynomial in lambda. That means this is a polynomial of very large degree, and you divide f lambda into that, then you have a quotient, a polynomial. If this is of degree 64 and this is degree 4, then this will be of degree 60, and the residual polynomial is what is left will be degree, if this is of degree n, this will be of degree n minus 1. This is the residual polynomial of degree n minus 1. Of degree n minus 1. This is characteristic polynomial degree n, and this we will call the quotient polynomial. This is not important for us to know what it is. Now this is a polynomial in variable, scalar variable lambda. Now the same thing can be written in terms of, suppose we have a polynomial, same polynomial in A, the matrix A, we get similarly QA FA plus RA, where the coefficients in all these polynomials are one and the same, except that in a variable lambda you get the matrix A. So whatever you do in the scalar polynomial, you can also do in the matrix polynomial. Now if you look at this form of this equation, we know that every square matrix satisfies its characteristic polynomial, characteristic equation. Therefore FA happens to be equal to 0. We just now saw if f lambda equals 0 for particular values of lambda, FA is 0. Now the difference between these two is this: f lambda is equal to 0 will be satisfied for particular values of lambda. So this particular equation will be satisfied for lambda equals lambda 1, lambda 2 up to lambda n, only for the characteristic values. This is not an identity, this is satisfied for particular values of lambda, the characteristic values or the eigenvalues. On the other hand, FA equals 0 is satisfied identically. Once you plug in the value capital A into this will be 0, the matrix A is equal to 0. So whatever a characteristic value satisfies in this equation, this matrix A satisfies here. So coming back to this, we observe that when you set up GA in this form QA FA RA, this will be identically 0, which means that G of A, whatever be the degree of this polynomial, can be simply written as equivalent to a polynomial of degree n minus 1. You may have G of A polynomial of degree 1000, but as long as the characteristic polynomial has a degree n, we can write this as equal to RA, which is of degree n minus 1. Now how do we, therefore whatever be the polynomial you are talking about, you can always write this in the form of RA, where the polynomial is at most of degree n minus 1. We can extend this further, we can even write for exponential, this need not be a polynomial, this will be a transcendental function which is equivalent to a polynomial of infinite degree, even then this is true. Now how do we calculate therefore the coefficients in this polynomial RA? Now for this you go back to this. Now this equation, if lambda equals lambda 1, lambda 2, suppose you substitute one of the characteristic values for lambda, then this becomes 0. That means G lambda will be equal to R lambda when lambda equals takes any one of the characteristic values. Therefore we can say that G lambda equals R lambda for lambda equals lambda 1, lambda 2 up to lambda n, because f lambda 1 is 0, f lambda 2 equals 0, f lambda 3 equals 0. This becomes 0 only for values of lambda equals one of the characteristic values. And after all, the form of R lambda is the same as form of RA, therefore GA can be written as RA. So given a given polynomial G lambda, you can substitute lambda equals lambda 1, lambda 2 and lambda 3 and evaluate the coefficients in R lambda. R lambda is a polynomial of degree n minus 1. So the general form of this will be the form C0 plus C1 lambda plus C2 lambda squared up to Cn minus 1 lambda n minus 1. So we have n coefficients. The R lambda is defined by n coefficients C0 to Cn minus 1. So given this G lambda, you can substitute lambda 1 to lambda n, and then you know this function, therefore you can evaluate this for different values of lambda. You got any equations, you can evaluate C1, C2, Cn, and that can be used to form this RA, and therefore GA can be evaluated. That is the approach that we take up. And whatever we have done can also be extended to a polynomial at infinite degree. In particular, if you have e to the power of a, that also can be written as C0 plus C1a plus C2a squared right up to Cn minus 1 an minus 1. This is also true. So we have to evaluate C0, C1, C2, Cn minus 1. We don't have to have an infinite series for e to the power of a. We don't have to do that. We can express this as a finite series of degree n minus 1. Now how do we calculate C0, C1, C2, Cn? We go back to this. If you have taken e to the power of lambda, that will be equal to, I am sorry, here I must write, because this is a matrix, I must write C0 times I. This is a constant, this is I, unit matrix. So if you take e to the power of lambda corresponding to G lambda, it is equal to C0 plus C1 lambda plus C2 lambda squared right up to Cn minus 1 lambda n minus 1 for particular, this equation is valid for particular values of lambda, whereas this equation is valid for identically. Here this is valid only for lambda equals lambda 1, lambda 2, lambda n, because this equation is valid because only when f lambda is 0, and that is true only for lambda assumes one of these characteristic values. So the approach is like this. If we want to express e to the power of a by means of a finite series like this, you have to evaluate C0 to Cn minus 1. That is n constants you have to evaluate. These constants can be evaluated by going back to the scalar equation, substituting lambda equals lambda 1 to lambda n. So e to the power of lambda 1 equals so much, e to the power of lambda 2 is equal to so much. You get n equations and you can solve for these n constants and use those constants in this finite series and get this. What we have done is for e to the power of a and e to the power of lambda, but in our system transition matrix we have e to the power of at. So the only difference is if you have e to the power of at, the matrix polynomial that we have to take into account is C0 t I plus C1 t a down the line to Cn minus 1 is a function of t a n minus 1. That is the only difference. So instead of being constants here, they will be functions of t. And to evaluate that C0 to Cn minus 1, those values, they are constants as far as a is concerned, but they are functions of t. So we take the corresponding scalar equation and write this as equal to C0 of t plus C1 t times lambda etc. Cn minus 1 t lambda n minus 1, and this is valid for lambda equals lambda 1 to lambda n. So we have n equations from this. So this is equivalent to n equations, because every time you substitute a particular value of lambda, you get one equation in the series. Any equations can be used to solve for n unknowns. What are the n unknowns? C0 of t right up to Cn minus 1 of t. So these n unknowns can be used, can be found out from this solution of this equation, and they can be used in this expression to evaluate e to the power of at. In our further work, we don't have to explicitly show this functional notation Ci of t. We know they are functions of t, therefore we may as well simplify our notation, write e to the power of at as c naught I plus c1a plus c up to cn minus 1 a n minus 1. Now an example will illustrate the technique that is involved, but the principle therefore is that we make use of the Cayley-Hamilton theorem and say that every square matrix satisfies its own characteristic equation, and therefore any higher power of a, even a transcendental function of a, can be essentially reduced to a polynomial in a of degree n minus 1. And to evaluate the coefficients of that polynomial, which is n coefficients, we go back to the scalar equation, and that scalar equation, corresponding scalar equation, is satisfied for n distinct values of lambda, which are the characteristic values. So you get any equations and use them to solve for c naught to cn n minus 1. We illustrate this for this particular situation, but you straight away notice what happens if some of these lambdas are repeated. If suppose lambda 1 equals lambda 2, then you don't have n eigenvalues but n minus 1 distinct eigenvalues. How do we tackle that situation? But that we will take up later, but first let us illustrate this procedure for the case where all the eigenvalues are distinct. As an example, let us consider the determination of e power at when A is the square matrix minus 1 0 1 minus 2. The first thing to do is to find out the eigenvalues. So to do that, we form the characteristic equation. So f lambda, which is equal to the determinant of lambda I minus a, which is of course the determinant formed by this matrix. So lambda minus a, the lambda I has diagonal entries lambda, and from that you subtract this A matrix. So this will become lambda plus 1, this is 0 minus 1 lambda plus 2. So that is the determinant formed by this matrix delta I minus A, and that will of course be delta lambda plus 1 times lambda plus 2, that is equal to 0. That is the characteristic equation. So the eigenvalues are two eigenvalues, lambda 1 is minus 1 and lambda 2 equals minus 2. So they are distinct eigenvalues, minus 1 and minus 2. So we keep that at the back of our mind. So we want to find e to the power of at. E to the power of at now is a square matrix of order 2, because A is a square matrix of order 2. Therefore the residual polynomial has degree 1. Therefore we write this as c naught I plus c1a. We take only the first degree because this is the characteristic polynomial of this is of degree 2. And we know that c0 and c1 are functions of t. We don't specifically exhibit that in that manner. We know that c0 and c1 are going to be functions of t. To evaluate c0 and c1, we go back to the scalar equation. E power lambda t will be equal to c0 plus c1 lambda, and this is not an identity, this is an identity. This will be used true only for, valid for lambda equals lambda 1 and lambda 2. So only for lambda has those particular values, this equation is true. So we substitute those values. Lambda 1 is minus 1, therefore e power minus t equals c0 minus c1, and the lambda 2 is minus 2, so e power minus 2t equals c0 minus 2c1. These are the two equations you get in terms of c0 and c1. You can solve this and you get c1 equals e power minus t minus e power minus 2t, and c0 as 2e power minus t minus e power minus 2t. So those are the two values, c0 and c1. Now you substitute in this equation, therefore you get this as, substituting c1 and c0 into this. So you have here really the first matrix is c0 0 c0. The second matrix is c1 times a. Therefore this A matrix every entry is multiplied by the scalar C1, therefore minus C1, 0, C1 and minus 2 C1, and you substitute these values in this and you finally end up with e power minus t 0, e power minus t minus e power minus 2t and e power minus 2t. So that is the final solution for e power at in this particular example. So the steps are straightforward. All you have to do is e power at must be expressed as a polynomial in a of degree n minus 1. To evaluate the constants that are involved, constants in terms of a, that's what I mean. They are of course functions of time. To go back to the scalar equation, and this equation is satisfied for characteristic values which you have to find out in the start to start with, and once you substitute the C coefficients can be evaluated, you substitute and then you get this final result. The work we have done so far was valid when we have n distinct eigenvalues. So by substituting each one of these in the scalar equation, we got n equations and enabled us to solve for the n coefficients, nc coefficients C0 to Cn minus 1. Now what happens if there are repeated eigenvalues? Suppose out of these n eigenvalues 2 or 3, a particular eigenvalue is repeated 4 times, then when you substitute that particular eigenvalue you get the same equation, therefore you do not get 4 equations corresponding to those 4 repeated eigenvalues. So how do you handle such a situation? Do we run out of equations? Do we have enough equations to solve for the n unknowns, n unknown coefficients, C coefficients? So we will see this does not create any special difficulty. So let case of repeated eigenvalues, let a particular eigenvalue lambda I be repeated r times. What does it mean? That lambda minus lambda I to the power of r is a factor of f lambda. So that this particular eigenvalue is repeated r times, therefore lambda minus lambda I raised to the power r is a factor of f lambda. So now when you form this scalar equation, e lambda t is the coefficient polynomial times f lambda plus the residual polynomial r lambda. You have f lambda is a factor lambda minus lambda I raised to the power of r. Now this is satisfied for lambda equals lambda 1, lambda 2, etc. up to lambda n, but some of them are of course not distinct, lambda is repeated n times. Okay, so we will say I will just leave it at that. Now when you substitute lambda I, then certainly e power lambda I t equals r times lambda I, because this becomes 0. But then what you can see is if f lambda is this particular factor, when you take the derivative of this, say d by d lambda of e power lambda t, if you take that, then you have q prime f plus q times f prime plus r prime, where the prime indicates the derivatives of the respective polynomials. So if f lambda has this factor, the same factor continues here, but it also continues here with a reduced degree. Lambda minus lambda I raised to the power of r minus 1 is a factor here. So this also, when you substitute lambda equals lambda I, these terms drop out and you have got r prime lambda I must be equal to d by d lambda e to the power of lambda t. That means when you substitute here, not only you get one equation from here, but if you take the derivative, then also you get a second equation. Like that you can go on up to higher derivatives. If you have this lambda minus lambda I raised to the power of r is a factor of r here, you can go on taking the derivatives up to the r minus 1th order, and then also that will you get an appropriate equation. That will be shown here. So you have got e power lambda I t equals r lambda I. Then you take the derivative of this. d by dt of e power lambda t, substitute the lambda equals lambda I, which means when you take the derivative of with reference to lambda, you get t times e power lambda t. When you substitute lambda equals lambda I, you get lambda. Right, and that will be, that means you have taken the derivative of this and substitute lambda equals lambda I, that is what you have here. This will become 0, this will become 0, and this will not become 0, therefore you get r prime here lambda I. Like this you can go on, you can take d r minus 1, d lambda r minus 1 e power lambda t, substitute lambda equals lambda I, that also will become r, the r minus 1th derivative of this, substitution lambda I, this one equation. Because even if you take the r minus 1th derivative, lambda minus lambda I continues to be a factor of these two, of such similar, all factors except this last one. So we now have, if you collect this, you have r equations, and these r equations will give you constraints on r, the coefficients. Therefore lambda, since the factor here is repeated r times, corresponding to this r terms in this f lambda, you get r equations. So we will never be in short supply as far as the number of equations are concerned, even if a particular eigenvalue is repeated, and you form the successive derivatives and substitute lambda I, you get the required number of equations. A example will illustrate this procedure very clearly. So let us do that example. Let us take the A matrix to be a matrix of order 3, 0, minus 1, minus 3, minus 6, 0, minus 2, 5, minus 2, and minus 4. Corresponding to this, determinant of lambda I minus a equals 0. It will turn out to be lambda plus 1 whole squared times lambda plus 2 equals 0. That means you have lambda minus 1, minus 1, minus 2. These are the three eigenvalues, and one particular eigenvalue is repeated twice, minus 1 and minus 1. So now let e power a t be equals c naught I plus c1a. Now since this is of order 3, we have to go up to the second power of a, c2a square. To evaluate c0, c1 and c2, we fall back on the scalar equation, e power lambda t equals c0 plus c1 lambda plus c2 lambda for lambda equals minus 1 and minus 2. So let us substitute minus 2 and get rid of that to start with. So e power minus 2t equals c0 minus 2c1, this must be squared, plus 4c2. That is one equation. And substitute lambda equals minus 1, e power minus t equals c0 minus c1 plus c2, that is the second equation. To get the third equation, you take the derivative of this with reference to lambda. So we get d by d lambda e power e lambda t, which is equal to t times e power lambda t, that if you take the derivative on the other side, you get c1 plus 2c2 lambda. And this particular equation is true for lambda equals minus 1, because that is the one that is repeated twice. Not for 2 lambda equals minus 2, only for lambda equals minus 1. So when you substitute here, you get a third equation which says, that is t e power minus t, t e power minus t equals c1 minus 2c2. That is the third equation. So you have two equations already from the straightforward procedure, by taking the derivative you get a third equation, t e power minus t equals c1 minus 2 c2. So using these three equations you can solve for c0, c1 and c2. The result will be c0 will be 2t e power minus t plus e power minus 2t, c1 will be minus 2 e power minus t plus 3t e power minus t plus 2 e power minus 2t, and c2 will be e power minus t plus t e power minus t plus e power minus 2t. So those are the three constants, and you substitute those constants in this equation. Constants, I am saying constants in the sense that they are independent of lambda or independent of a. Substitute c0, c1 and c2 in this equation and you can evaluate e to the power of at. The details I will omit. So notice that since this particular characteristic value is repeated twice, you get t times e power minus t. Those terms are present here. So if it is repeated 3 times, you get t square terms also will be present, t square e power minus t will be present. This is just like having multiple poles in the case of Laplace transform solution. Okay. Now let us look at the, with this background, let us look at the general solution of the state and output equations. Now let us look at the solution of the general equation, state equation, not the homogeneous equation as we have considered earlier. To do this, let us multiply by e power minus at right through. You have e power minus at times x dot. As transferred to the other side, e power minus at times a times x equals e power minus at times bu, where u is a function of time. Now these two terms on the left hand side can be written as d by dt of e power minus at times x, because this is the derivative of a product. Therefore the derivative of e power minus at is e power minus at times minus a, so times x, plus e power minus at times the derivative of x, which is this. So these two terms can be put in this form. This will be of course e power minus at times b u of t. This u is a function of time. Since this is the derivative of this is equal to this, e power minus at times x of t, this is x of t of course, x of t must be the integral of that. So you can write e power minus at times x of t is the integral of this. Now that integral we have to, the right left hand side is a function of t, therefore we can introduce a dummy variable for the integration. You can write e power minus a tau b u tau d tau 0 to t. That is what you are having, because after all this is a function of time and the variable of integration should be something other than t. I put like this. But we also have an arbitrary constant, because after all the derivative of this is equal to this. So when you are integrating you must put something else, and that is a vector. E power minus at times x is a vector, and that must be equal to, suppose we substitute t equals 0. If substitute t equals 0, the upper and lower limits are the same, so therefore this becomes 0, and here e power minus at, which is of course equal to unit matrix, therefore this becomes x0. So to evaluate this thing, the arbitrary constant that is involved here is x0. So that takes care of the arbitrary constant that comes in the integral. So now we can write the solution for xt as 0 to t. You can now introduce this inside e power at. So you have e power at, that means you multiply right through by e power at. So e power at minus tau b u tau d tau plus e power at times x. So you observe that this is the 0 input solution, and this is the solution that comes because of the presence of the input. This is something which you already know, that is up for xt. This is the extra term that comes about because of the presence of the forcing function. we can put this in a more compact fashion, recognizing this to be something similar to your convolution integral, except that matrices are involved, otherwise it is the same. So I can write this as e power at convolved with dut. After all, in the form wise is exactly the same as this. So I can write this as e power at convolved with but plus e power at x0. So using this information, we can now know the output is Cx plus du. So we know the solution for x, we substitute this here, you get C e power at times x0 plus C e power at convolved with but plus, of course, you have got dut. So this is the final solution for y. C e power at x0, C e power at convolved with but times dut. The meaning of this convolution is this integral. Now you compare this with the Laplace transform solution. You notice that in the Laplace transform solution we have y of s equals c times si minus a inverse x0 plus c times si minus a inverse b us plus d us. Since we already noted that e power at and si minus a inverse form a Laplace transform pair, so you can easily see that the Laplace transformation of this is indeed this, because this the only function of time is this e power at. So its Laplace transform is equal to this. This is a constant and this is a constant, of course, constant vector. And here you have got the convolution of two time functions e power at and ut, therefore you have got the product of the corresponding Laplace transforms bu minus ac dus. In working out numerical examples, you can put the star here, either here or here, whichever is convenient for you, because after all this is a constant that can be pushed either this side or that side. You can c e power at, this is also equivalent to, you can write this if you wish, c e power at b convolved with ut, makes no difference. So this is the solution in the time domain, which corresponds to the solution in the Laplace transform domain. So in fact, since you know the solution in the Laplace transform domain, you could have found out the time domain solution by taking the inverse Laplace transform of this, you would have ended up with the same thing. Right. So this gives you a very compact way in which you can find out the output quantities. It is usual to write e power at as phi of t is e power at. So you can put this as c phi t convolved with but. So in which case this term will be c phi t convolved with. This is another way of writing the equations. In the next lecture, we would consider working out a numerical example illustrating these various concepts. So what we have done today is we started out with the system transition matrix, also simply called the transition matrix e power at, and we said that e power at can be evaluated in several ways. One is using the Laplace transform approach. Si minus a inverse happens to be equal to e power at, is the Laplace transform of e power at or the transitional matrix. An alternative way of working out in time domain would be take a finite series approximation for e power at by taking the infinite series and truncating at a particular point. We said this does not recommend itself because we do not get a closed form expression, and it may be suitable for computer working, but not for when you want to do it analytically and you want to arrive at a closed form expression. A third method is to diagonalize the A matrix, and the diagonal matrix that turns out will be one in which you have got the eigenvalues along the main diagonal, and the transformation matrix T and T prime will be associated with the eigenvectors. And once you have done this, I mean, there are different mathematical methods of finding out the transformation matrix needed for this job. And once we have the transformation matrix, evaluation of e power at is very convenient. We have given the form for this, but we have not worked out this particular method in great detail. But the method that we have discussed in some detail is the one which is based upon the Cayley-Hamilton theorem, which states that every square matrix satisfies its own characteristic equation. Therefore, if f lambda equals 0 is the characteristic equation, fa equals 0 is also satisfied for identically for a given square matrix. Now, this enables us to write any transcendental function of a, any higher degree polynomial of a, as equal to a polynomial of degree at most n minus 1. So, to find out the coefficients involved in this reduced order polynomial, we go back to the scalar polynomial in terms of lambda and substitute that particular equation. The scalar polynomial is satisfied for particular values of lambda, which are the characteristic values. We substitute those values and you get enough number of equations to evaluate the various constants that are involved in the expression for the residual polynomial for e power at. We also saw that even when one of the eigenvalues is repeated several times, we can still get enough equations. We will never be in short supply as far as the number of equations is concerned by taking the derivative of e power lambda t with reference to lambda, and then because a particular factor is repeated several times in f lambda, by taking successive derivatives, that factor still remains up to if the original factor was of degree r, up to the r minus 1th derivative, that factor remains, at least r minus 1th derivative, it will be a linear factor, not a higher power, and therefore using that particular property, if there is a factor repeated r times, we get additional r equations. So with this we were able to get enough equations to solve for all the coefficients in the residual polynomial of degree n minus 1, and therefore we can evaluate e power at. We worked out a numerical example to show this, and then once we know how to calculate e power at, we can give the general solution for the state vector, and from that the output vector, and the final solution will be of this form, which involves the 0 input solution, this is 0 input solution, this is the 0 state solution, this part is the 0 state solution, and we saw that it corresponds with the solution that we already obtained in terms of Laplace transformations that we already discussed in the last lecture. We will work out a numerical example of finding out the solution in time domain based on this equation in the next lecture.